Now that you understand what it means for a plan to be a solution to an STN planning problem, we can turn to the algorithm that finds these solutions. So we will now look at the planning procedures that refine task networks until we have solutions to our planning problems. And here is the pseudocode for the ground TFD procedure. TFD here stands for Total Order Forward Decomposition. This procedure deals with total order problems and domains only. It does a forward decomposition, meaning it always starts from the initial state and tries to build the plan up from there. And the D is simply for decomposition, so it uses methods to solve STN planning problems. And the input to this recursive function is a planning problem. So we have an initial state, a total order task network, a set of operators, and a set of methods. The outline of the procedure then follows exactly the definition we've just seen. So first we have the case where we deal with an empty task network as input. Then we have the case where the first task in the given task network is primitive. And finally we have the case where the first task in the given task network is non-primitive. The simplest case, where k is equal to 0, that means we have no tasks in our initial task network, and that means the empty plan is a solution for this task network as given in the definition. Then we're dealing with the case where t1 is primitive. That means there must be an operator that has the same name as this task, and that means there must be actions that are instances of this operator and that have the same name as the task instantiated with some substitution sigma. And these actions may be applicable in our state S. So we're only looking at actions that are applicable in our state S. And that's what we do here. We compute the set of actions that are unifiable with our first task, T1, and are applicable in S. And that's the set actions here. If this set is empty, then there is no way to accomplish this primitive task, and that means we can return failure or we go back to the nearest backtrack point. Otherwise, we can choose one of these actions from our set of actions and refine our plan in that way. Note that this choosing here is a non-deterministic choice point, so that means we may have to backtrack here and try a different path if we fail in the current branch. Then we apply the definition of a solution here that said a plan is a solution to a planning problem if a modified plan is a solution to a modified planning problem. And we do this by recursively calling ground TFD here with the modified planning problem. And the problem is modified as follows. We first compute the successor of the initial state given our chosen action, and that's our new initial state. Then we take the remainder of our task networks consisting of the tasks T2 through Tk and instantiate those with our new substitution sigma. Note that T1 is no longer in this task network, and the set of operators and methods remains the same. Of course, this procedure may return failure, and in that case all we have to do is pass the failure back up because this branch in our search does not give us a solution. Otherwise, the returned plan is part of our solution, but our action that we've just chosen to refine the plan must be added to the plan, and in this case it must be added at the beginning of the plan. And then there's the third alternative path in this algorithm where our initial task T1 is not primitive, and that's what we have here. And in this case what we have to do is compute the set of methods that are relevant for this given task under some substitution sigma, and that are also applicable in our initial state given as part of the planning problem. And this is the set of methods that we can use to refine our plan. And again, if this set of methods is empty, that means there is no way to refine the first task in the network, and that means we can return failure. There's no solution in this branch of the search tree. Otherwise, we choose one of the methods, which means we have a non-deterministic choice point again. We have to come back here if we fail in the current branch and choose a different method from our set. So we choose a method and a substitution, and we try to refine our plan with that method. And in the total order network, this is quite simple. We take the set of tasks minus the first task. We remove that from our sequence of tasks, instantiate those with our substitution, and prepend this with the subtasks of our method. That gives us a modified network that we can now test to see whether this is a solution to our planning problem. And we do this by again calling the function groundTFD recursively, given the same initial state, our new plan that we've just created, and the operators and methods from the original planning problem. So what this procedure does is take this task network, look at the first task in the network. If this is a non-primitive task, it will go in that final branch here, where it replaces the first task with the subtasks in a method that is applicable and relevant here. And then eventually this will get to finer grained tasks. We will get to the second part here, where the first subtask in one of these methods was primitive, and then we get to this part, and we remove that task and recursively call this function, and hopefully finally we end up in the first branch where we've removed all the tasks from our network and have a plan that is a solution to our planning problem. And here is an example from the DWR domain that shall illustrate this algorithm. We start with the same task we've seen before. We want to move the stack that is currently in pile P1 to another stack Q, where Q is a variable, so it is unspecified. So the algorithm first takes the first task in the sequence of tasks and tests whether it is a primitive or a non-primitive task. In this case, it is a non-primitive task, which means we have to compute the set of all relevant and applicable methods and choose one of those. And that's what I'm doing here. I'm choosing the method recursive move from pile 1 to pile 2, where we're moving container 1 from container 2 as the first part of this method. Note that I'm making all the right choices here that will not require me to backtrack anywhere. Now we can apply this method to decompose the first task in our task network, and that gives us two new subtasks, namely moving the topmost container from pile 1 to pile 2, and moving the stack from pile 1 to pile 2, so that's recursive again. Notice that it's ground here in this method. P2 is instantiated, and it is instantiated in our subtask as well. Then the procedure again takes the first subtask in this new network, which is the move topmost task. And because this is a non-primitive task, we end up in the third part of the algorithm again, which means we choose a method. And here I'm choosing the take and put method with some appropriate arguments. And I'm using that to refine this task, giving me two new subtasks. And they're gray here because they are now primitive subtasks. So again, the procedure would go through the recursive call, take the first subtask in this network, which is now the take, crane, at location, and so on subtask, and I'll have to find an action that matches this task. And of course, there is an action that immediately matches this task, so I can add this to my plan. Then I go to the next first subtask. Remember, we have removed this task now. So the next first subtask is this put task here. And again, there's an action that directly matches this task. So I can remove this from the task network and look at the next first task, which now is this move stack task here. And again, we end up in the branch where we have to choose a method that refines this task, this non-primitive task. And now we're choosing recursive move here again with different containers. And if we refine this task, we get as the first subtask move topmost and then move stack again. And we go through the loop again. The first subtask is now move topmost. And we use a take and put method to refine this task, giving us two primitive tasks. So we go through the primitive tasks again, trying to find actions for those tasks, and we find an action that matches this task, and we also find an action that matches this task. And that leaves us with this task here as the new first task in our network. And again, this is a non-primitive task, so we've got to find a method and use this method to refine the task into two subtasks. Where move topmost is now the first one, so we go again into the recursive call. We find a take and put method that matches this task, refines it into two primitive tasks, and again there are actions for both of those. So we turn to the final task here, which is moving a stack from P1 to P2, but now if I had shown you the state, you would see there are no containers in here, so we can apply the no move method, and that gives us the empty plan as the result. And this is essentially how our ground TFD algorithm works.